G'day guys, and welcome to our lesson on gravitational fields. Now there's two ways to describe what a gravitational field is. The first is the amount of force per kilogram that gravity is applying on an object, and the second is how fast gravity is accelerating an object towards the larger mass. Both of these descriptions are equally valid, and we'll see that they're both actually connected in a second. First of all, let's recap what exactly the gravity force is. So we know, if there are any two objects in the universe with mass, like this one big M and this one little m, they will attract each other with the force of gravity. And the force of the big M mass on the little m mass is given by this Fg arrow, and the force of the little m mass on the big M mass is given by this Fg arrow. And according to Newton's third law, these arrows are equal and opposite. The magnitude of this Fg force is given by this equation. Fg is equal to the gravitational constant multiplied by the big M mass in kilograms multiplied by the little m mass in kilograms divided by r, which is the distance between the center of the two masses, squared. And of course r is in meters. And the gravitational constant never changes. Other things can change. The mass of one object can change with the mass of the other object, and the distance between them is changing. Actually, in a lot of cases that's changing rapidly, but g is just always equal to 6.67 times 10 to the negative 11. So this will be on your cheat sheet. Now, if I were to say this object is falling towards this object, it's implicit that this object has some kind of gravitational field which is pulling in everything around it. But if I wanted to talk about the strength of that field, let's say I try to talk about the strength of it by saying Fg is however big. That Fg term is dependent on the mass of this small object. So in a way, that description is not very good because it's dependent on the mass of the object which I'm chucking into that field. It would be better if I had a description for how strong the gravity was at different points around here, if it didn't involve the mass of an object, if it was completely independent of the mass of the object thrown in there. And the way we do this is, we say if Fg equals big G times m on r squared, then if we divide by the mass, we get just the gravitational field strength. And we can actually graph it. The first thing I want you to notice is if we graph G on the vertical axis up here, G, and R on the horizontal axis, this looks a lot like what you'd see in maths, a graph of y equals k, a constant because these two things are constants, over x squared, which looks a bit like that there. So that is in fact the shape of the graph we're going to draw on the axis down below. Now the first thing we need to realize is that for this mass here, you can't go any closer to this mass than big R, the radius of the mass, because once you do that you're actually going inside the surface of this mass, and the equation no longer applies because, well, the best way to think of it is some of the mass is behind you pulling you back, so you can no longer use that big M. So before you get to this R value here, the gravitational field actually proceeds in a straight line upwards like so. But once you get outside that radius of the planet, we'll say it's a planet, it obeys that shape I showed before, G equals K on R squared. So it looks a bit like this. Drops down, and there's an asymptote. So what this is telling you is if you're a little spaceship over here, and you're approaching this planet here, you'll find the gravity force is not very strong. And in fact, if you were infinitely far away from it, you'd find the gravity force approached zero. But as you get closer here to the planet, the gravity force increases and you start getting pulled. If here was a little pull, here is a big pull. And that's your acceleration towards the planet. And then the maximum pull you can get occurs right before you impact the planet here. And of course, this is basically referring to what would happen if you tunneled into the planet. But the important thing to remember is, this is not a measure of the force. It's a measure of the acceleration. So if we say g equals 5 along this line here, that means when I come to this distance from the planet, r, I should be accelerating at 5 meters per second squared towards that planet. But the actual force is given by F equals the mass times my acceleration. So this graph here with g gives me the acceleration, so g or a. But if I want to find the force, I have to multiply by the mass. So say I was here, and the gravity force was 5, and my craft was 2,000 kilograms. The actual force of gravity would be not g equals gm on r squared, but the force of gravity equals gm on r squared multiplied by my mass. Or in this case, 5, which is gm on r squared, multiplied by my mass. So 5 times 2,000, 10,000 newtons. This bit of information demonstrates something very important about the area under this graph. So say I started out on the Earth's surface, and I want to get to this point here. We'll call that r dash. The area under this graph has some significance. We basically know that work equals force times distance. And if you're on the planet Earth and you want to get off, you've got to do a lot of work against gravity. The area under a force times, well, radius is basically distance. Force times distance graph is the energy. But since this is the area under an basically acceleration times distance graph, then the area does not equal the work. But if you multiply the area by the mass of the object you're lifting out, that's when you do get the work you need to do against gravity. So the first thing you need to know is if you're moving away from a planet, then basically gravity is doing work against you. So if you start off with a lot of kinetic energy, that kinetic energy will go down whilst your gravitational potential energy will go up. So intuitively, if you throw something very quickly off the Earth's surface, it'll slow down as it gets further away. And that's because the kinetic energy that it did have on the Earth's surface here is being exchanged for gravitational potential energy. And the amount that is exchanged, this loss in kinetic energy, is given by that area under there multiplied by the mass. However, if you start off like this rocket ship and you turn off your engines and you just drift into the Earth's surface here, you're moving not in this direction here, but in the opposite direction. So we'll say we'll move from, that's R2, that's a bad place to put the 2, R2, this is R3. Say I move from here to here. The area under here, if I multiply it by the mass of my spacecraft, I get the work. Whoops, sorry, did I say moving from R2 to R3? I mean, that's R3, and that's R2. So if I'm moving from R3 here to R2 here, if I take the area under this graph and multiply it by the mass of my spacecraft, I get the work done by gravity on me. And since I'm moving towards the planet, and gravity is acting in the same direction as I'm already moving in terms of velocity, my kinetic energy is going up, whereas my gravitational potential energy is going down. So this is towards the planet, and this is away. And the amount of area here multiplied by the mass gives me exactly how much kinetic energy I've gained in that time. Now, the last thing I want to talk about is this little peak here. We said once you reach the radius of the Earth's surface, gravity has reached a maximum, because once you're inside, you're effectively reducing the mass of the object that's pulling you. But there is an object in the universe that has a very, very small radius, that's in fact infinitely small. And so this graph continues to go up to an asymptote there. And that object is known as a black hole, where at the singularity, gravity is theoretically infinite. But one thing we should recognize about a black hole is if you have a black hole the same mass as a star, even though the black hole, once you get very close, the gravity becomes, why would I use this word, astronomically large, at the same distance out here, if the black hole has the same mass as a sun, it'll also have the same gravitational attraction. So, gravity, the gravitational force, is a function of the mass of one object, the mass of another, over the radius squared. But the acceleration due to gravity does not have to take into account the mass of the smaller object that is experiencing the acceleration. The area under the gravitational force graph multiplied by the mass gives you the work, and depending on the direction, it could either be taking away from your kinetic energy or adding to your kinetic energy. Look to the example videos to see a few questions that are solved using this method.